Newton's third law of motion is one of the most important principles in physics. It states that for every action, there is an equal and opposite reaction. That means forces always come in pairs. Whenever one object pushes or pulls on another, the second object pushes or pulls back with the same strength, but in the opposite direction. This process is called an interaction. An interaction happens anytime two objects apply forces on each other at the same time. One object creates the action force and the other responds with the reaction force. These two forces are always equal in size but opposite in direction. To give a simple example, imagine pushing on a wall. Your hand pushes against the wall, and at the same time, the wall pushes back on your hand with the equal force. You don't move the wall, but you feel the force pushing against you. Newton introduced this law back in 1687 in his famous book, Principia Mathematica. At the time, this was a groundbreaking discovery. It showed that every push or pull is always met with a matching response, which was a powerful idea for science. This law became one of the building blocks of modern mechanics, engineering, and technology. Without it, we wouldn't fully understand how motion works, from the way we walk to the way rockets launch into space. One of the fields most directly connected to Newton's third law is biomechanics, which is the study of the forces acting on the human body and how the body responds with the motion. Biomechanics uses Newton's third law to explain how we move every single day. For example, when you walk or run, your foot pushes backward and downward on the ground, and the ground pushes forward and upward on your foot with equal force. That opposite reaction is what propels your body forward. Without this reaction, you wouldn't be able to take a single step. Jumping is another example. When you push down hard on the ground pushes you upward with equal strength, launching your body into the air. Swimming works the same way. Your arms and legs push water backward, and the water pushes your body forward, allowing you to glide through the pool. Athletes rely on this law constantly. A basketball player pushes against the court to sprint or jump higher. A soccer player kicks the ball forward and feels the equal and opposite reaction in their leg. Even in weightlifting, the barbell pushes down on the athlete's hand with the same force that they push upward. So biomechanics shows us that Newton's third law isn't just something in a textbook. It's what makes every movement possible, from the simplest step to world-class athletic performance. One of the most important scientists connected to Newton's work is Galileo Galilei, who lived from 1564 to 1642. Galileo is often called the father of modern science because he transformed the way people study nature. Interestingly, Galileo started out studying medicine at the University of Pisa, but he switched to mathematics and science, where he made discoveries that completely changed physics. As a professor, he taught geometry, mechanics, and astronomy, all subjects that tied directly to forces and motion. Galileo was different from many scientists of his time because he believed in careful observation and experimentation. Instead of trusting old theories, he tested ideas, measured results, and repeated experiments. This hands-on approach helped create what we now call the scientific method. His research topics include falling bodies, inertia, projectile motion, and pendulums. For example, Galileo proved that all objects, no matter their weight, fall at the same rate in the absence of air resistance. He also discovered that pendulums swing in a regular rhythm, which led to more accurate clocks and showed that motion follows predictable patterns. But Galileo was also famous for his work in astronomy. Using his improved telescope, he discovered the 4 largest moons of Jupiter, which are still called the Galilean moons today. He also supported the idea that the Earth moves around the sun, not the other way around. This idea went against the teachings of the Catholic Church at the time, and as a result, Galileo faced a trial and spent his later years under house arrest. Even though he faced controversy, Galileo's discoveries about motion and forces directly influenced Newton. In fact, Newton's third law of motion was built on the foundation that Galileo created. Galileo showed that motion follows natural laws, and Newton expanded those ideas into 3 famous laws of motion, including the principle that every action has an equal and opposite reaction.
Hey everyone, my name is Chance, and today I'll be talking about Newton's law of motion, the rules that explain pretty much how everything moves. Newton's third law says every action has an equal and opposite reaction. Basically, whenever you push something, it pushes right back the same force. You see it when a rocket blasts off, the engines push gases downward, the rocket pushes the chute upwards, or when a swimmer pushes water back, the water pushes them forward. Engineers even use this law to design better and safer mechanics. Now, in physics, a force is just a push or a pull that can change how something moves, the direction it's going, or even its shape. We measure force in newtons. That's how strong that's how strong the interaction is. Thinking about pushing a box across the floor, or gravity pulling everything toward Earth. Newton's law matter because they explain what's really going on when things move. The first law shows why we wear seatbelts. Objects in motion want to keep moving. The second law says the more force you use, the faster it goes, like kicking a soccer ball. It goes harder, it makes it fly farther. And the third law is what gets us walking. Our feet push the ground, and the ground pushes us forward. These laws show up everywhere in sports, driving, rockets, and just everyday life. And I think if we didn't have them, we wouldn't be in a position where we are right now. So, yeah, basically, Newton basically gave us the blueprint on every motion and force and all those things. So, thank you for listening. Fire Chance again. And today we're talking about my related fields, which is engineering for my topic. The definition is Newton's third law states that for every action there is an equal and opposite reaction, like I said in the last slide. This means that whenever one object applies a force on another, the second object pushes back with the same amount of force in a different direction. So they just kind of collide, and work together. For example, in engineering, I have rockets and jet engines, are designed around this principle. As hot gases are forced out of the engine in one direction, an equal and opposite force pushes the rocket or the jet forward, allowing it to move through the air and into space. My example in structures is bridges, buildings, and other structures are also demonstration of Newton's third law. The weight of the structure pushes down on the ground, and the ground pushes back up with equal force. Engineers use this concept to design safe and stable systems that can support heavy loads, and that helps us with everyday life, with buildings, trucks, cars, all that. You know, basically, the force that goes down, another force is going to go back up, and it's what keeps us on our heads and toes. Thank you for listening. Hello, everybody. My name is Chance, and this is my relevant scientist, Albert Einstein. Albert Einstein was born in 1879 in Ulm, Germany. Einstein was a curious child, and he always wondered about math and science from a young age. He once worked at a patent office before becoming a professor. He moved to the U.S. during World War II and later worked at Princeton University. He died in 1955. His educational facts are Einstein studied physics and math at the Swiss Federal in Zurich. As a teacher and researcher, he focused on relativity and quantum theory. He encouraged imagination and problem solving. which inspired many future scientists and engineers today. I think that Albert Einstein was a very, very genius and a very experimental person. I think he think outside the box every single time. And a lot of people didn't agree with that. A lot of people did, but the thing with Einstein, I think, is that he didn't really care about what the critics said, or he didn't really listen to what, you know, people had to say about him. He just kept trying to improve and learn every single day. His research states that he created the theory of relativity and a famous equation E-mc, showing the link between mass and energy. He also explained the photoelectric effect, proving light acts as particles, which helped create quantum physics. He won the Nobel Prize in Physics in 1921. His fame is that, honestly, he's one of the most, if not famous scientists ever. I mean, who doesn't know about, Albert Einstein? But Einstein quickly became one of the most famous scientists in the world. His discoveries changed how we understand space, time, and energy. Beyond scientists, beyond being a scientist, he spoke out for peace, education, and human rights. I think, honestly, Albert Einstein is one of the greatest geniuses ever to live, and I really appreciate what he's done for what our future holds now. And I think he was a pretty cool guy. He could have been a little bit crazy. He could have been out of his mind a little bit, but I think as a scientist, you have to be a little bit out of your mind to figure out what you want to do in that kind of career. And honestly, just proving himself was crazy enough for other people, but he did what he had to do. And I think, like I said, his inventions and discoveries led us to what we are and how we think today. So, thank you.
Newton's third law of motion has significant applications in physics, engineering, and mechanics. It explains why forces are always in pairs. When one object applies a force, another object applies an equal and opposite force. Engineers utilize this principle to design stable machines, engines, and buildings that function properly due to reactive and balanced forces. According to Newton's third law, a force pair consists of two forces that are equal in magnitude but opposite in direction. These forces act on two different objects at the same time, ensuring that every action force has an equal and opposite reaction force. Newton's third law of motion is based on the principle of conservation of momentum and is demonstrated by the interactions of objects in the natural world. The third law demonstrates that all forces happen in pairs, allowing a physical system to remain balanced throughout the interactions. The third law is reinforced by experimental evidence and in physics is the basis of motion, collisions, and mechanical balance. Robotics is a branch of technology and engineering focused on designing, building, and programming robots and machines that can perform tasks automatically or with human control. Robotics use Newton's third law of motion to control interactions between robots and the environment. When a robot applies force to an object, the object exerts an equal and opposite force back. It is important for engineers to understand these forces because it helps them design robots that move efficiently and maintain balance during tasks. People depend on robotics to improve efficiency, safety, and precision in daily life and industry. Robots assist in manufacturing, performing surgeries, and exploring environments that handle repetitive or hazardous tasks, reducing human effort, error, and risk while increasing productivity and innovation. Robert H. Goddard was born in 1882 in Massachusetts. He was an American physics engineer and inventor. He was recognized as the father of modern rocketry. In 1926, Goddard successfully launched the world's first liquid-fueled rocket. He earned his Ph.D. in physics from Clark University in 1911, where he later became a professor. It was during his time at Clark that he conducted many of his early experiments in rocketry, combining teaching with groundbreaking research. Goddard's research focused primarily on rocket propulsion, and he was a pioneer in exploring how rockets could be used to reach high altitudes and eventually outer space. His work included both theoretical studies and practical experiments. Goddard is famous as the father of modern rocketry. He gained recognition for launching the first liquid-fueled rocket in 1926, a groundbreaking achievement that laid the foundation for space exploration.
Back in the 1600s, Sir Isaac Newton worked in his home study. His lab wasn't anything fancy like we have today. He used candlelight, wooden tables, and handmade pendulums made from string and metal spears. It was quiet and peaceful, but also really basic with no precise measuring tools. Newton spent a lot of time experimenting with pendulums to study collisions. He built wooden rams and used small cars to see how pushing one object caused another to move. One of his famous experiments involved swinging pendulums so that one ball hit another. He noticed that when one ball moved forward and struck another, the second ball moved backward with equal force. This led to his idea that for every action there is an equal and opposite reaction, the foundation of his third law of motion. Of course, Newton faced a lot of challenges while experimenting. He didn't have any advanced tool. Everything he used was handmade from wood, string, or metal. That meant friction and air resistance often messed up his results. Without precise instruments, it was really hard to prove that every action caused an equal and opposite reaction. On top of that, Newton had no safety equipment or lab standards. He worked alone with heavy spears and small cannons, which could be dangerous if something went wrong. And since there were no calculators or computers, Newton had to do all of his math by hand, every equation, every measurement, all written out manually. It made recording and analyzing data slow and exhausting, but despite all of those difficulties, he still managed to form laws that became the foundation of physics. Newton's main goal was to understand how forces cause motion and how objects react when they collide or are pushed or pulled. He intentionally studied motion and collisions to find consistent patterns. His discoveries were not accidents. They came from careful observation, testing, and reasoning. Newton's work was meant to help scientists and engineers better understand motion mechanics, and even astronomy. His third law of motion helped future researchers build on his ideas, from studying planets to designing new machines. So his motivation wasn't just curiosity. It was about understanding the laws that control everything around us. See the wall? Even though I'm pushing on the wall is pushing back with equal force. This is what Newton was curious about when studying motion and collisions. Newton's third law of motion gave scientists a new way to understand how forces work. It explained why every action creates an equal and opposite reaction, and that understanding immediately advanced physics. His discovery helped scientists accurately calculate motion, momentum, and balance from the first time. This law became the base of what we call classical mechanics, basically the physics that explains how objects move and interact in our everyday world. It also led to progress in areas like motion studies, collisions, and engineering, allowing science to grow far beyond what was possible in Newton's time. Now, let's fast forward to today. Modern university physics labs look nothing like Newton's old study. They're clean, open, and filled with metal workbenches, computers, and digital tools. Students now use sensors, lasers, and air tracks to study motion and collisions. Everything is carefully organized for accuracy and safety. When studying Newton's third law of today, students might place two gliders on a frictionless air track. When one glider pushes the other, sensors instantly record the equal and opposite forces, and computers graph the results in real time. This setup proves Newton's law with exact precision and something he could only dream of back then. Modern labs are much more advanced and safer. Instead of candles and string pendulums, scientists now use high-speed cameras, laser, and motion sensors to measure even the smallest changes. Data is automatically collected by computers, which eliminates human error and saves time. Students wear goggles, like so, follow strict lab rules, and use safety barriers to avoid injury from moving objects or machinery. We also have software that can instantly calculate reaction forces and plot data into graphs. So while Newton had to spend hours doing math by hand, we can get results in just seconds, making experiments faster and more accurate than ever. Newton's third law is still incredibly important today. It's the principle behind rockets, jets, and even drones. Every spacecraft launch depends on action and reaction. As exhaust gases push downward, the rocket lifts upward. Aerospace engineers use this law to design rocket engines, propellers, and propulsion systems for all types of flight. The law helps us understand how planes move forward, how jets create thrust, and how rockets escape Earth's gravity. So even though Newton discovered it hundreds of years ago, his third law continues to shape our world from airplanes to space travel. Looking into the future, scientists are developing even more advanced propulsion systems using Newton's third law like ion and plasma engines. These systems push tiny particles backward to move spacecraft forward efficiently, allowing us to travel faster and farther into space. The hope is that one day space missions will be faster, cleaner, and more affordable thanks to new technology built around the same principle Newton discovered so long ago. For every action, there's an equal and opposite reaction. Newton's third law continues to guide us, not just in physics classroom, but in the future of space exploration.
Hello, this is Chance, and I'll be going over my original process, which is water jet reaction study. The water jet reaction study is a great example of Newton's third law. Every action has an equal and opposite reaction. When water is pushed out in one direction, it creates an opposite force that pushes the object the other way. This same principle explains how rockets launch or how turbines spin. The experiment helps connect Newton's theory of motion to what we actually see happen in real life. For my second slide, my original difficulties is air resistance and friction. Air resistance and friction are both forces that work together against motion. Air resistance shows objects moving through the air, like when a parachute opens. Friction happens when two surfaces rub together, and that rubbing creates heat and slows movement. Engineers use this understanding to improve how cars, planes, and machines works, make them faster, safer, and more efficient. For my third slide, original motivation, I have connecting Earth and space physics. The motivation behind studying Newton's third law was to understand how motion and forces work everywhere, on Earth and in space. The same idea that explains walking or swimming also explains how rockets take off. Knowing that every action has an equal and opposite reaction helps scientists and engineers develop propulsion systems that work even in zero gravity. For my fourth slide, original benefits, I have scientific advancement in education. Studying Newton's law of motions gave scientists a stronger foundation. They helped shape physics, engineering, and technology as we know them today. These ideas made it possible to design engines, aircraft, and safer structures. In schools, they teach students how motion and energy interact, inspiring curiosity, problem solving, and innovation that continues to drive progress. For my modern process, I have high-speed cameras and digital tracking. Modern research used advanced tools like high-speed cameras and digital tracking systems to study how motion in detail. These cameras capture thousands of frames per second, letting us see movement too fast for the human eye. The tracking software measures speed, direction, and force with precision. This technology connects classic physics principles to modern day analysis. For my modern differences, I have data collection and sharing. Today, scientists collect and share data how much faster than ever before. Digital sensors and information instantly, and researchers across the world can share their results online. This allows scientists to collaborate in real time, compare experiments, and refine their work more efficiently. Modern technology has made studying physics more connected, accurate, and transparent. For modern benefits, I have automotive and safety engineering. When automotive and safety engineering, Newton Third's law plays a huge role. Engineers study how forces act during crashes and acceleration to design safer and stronger vehicles. By understanding reaction forces, they can create a better braking systems, airbags, and structures that protect passengers. These principles help balance performance with safety and innovation. For my last slide, future expectations, I have robotics and artificial intelligence. The future of studying motion lies in robotics and artificial intelligence. Robots rely on Newton's laws to move and balance, while AI helps and analyze and adapt to changing forces. Combining both technology leads to smarter, safer, and more efficient systems, from space exploration to everyday automation. The same principles that launched rockets now guide intelligent machines that keep learning and keep improving.
The original process. The laboratory settings utilized a dynamics track that was angled, dynamics carts, force sensors, pulleys, strings, and masses weights. The major purpose of the equipment was to measure forces acting on the cart and to engage in Newton's third law. This, of course, involved attaching masses together with a string that passed over the pulley to accelerate the cart up to the ramp. Usually an inclined plane and lab cart, a motion director, a meter stick, a proctor, a computer with data collection software are used in the lab. Pulley, strings, and masses are also included for application of force. The initial laboratory arrangement was a tangible one composed of sloped surfaces, miniature vehicles, ropes, heavy objects, measuring sticks, and timepieces, which relied on the applications of physical measurements and watching. Original difficulties. At first, the implements consisted of the inaccuracy of equipment, frictional errors, and the isolation of researchers, and the absence of peer reviews for validating the experiment's findings. Safety issues in the inclined planes and carts experiments included a risk of carts slipping, falling weights, pinched fingers from strings or pulleys, and potential instabilities of the inclined planes. Problematic equipment, incomposed pulleys frictions, non-uniformly sloped surfaces, cartwheels that were not smooth enough, incorrect mass determinations, and also either stretched or broken strings that were used throughout the experiment. Among the issues related to information processing were manual timing errors, misreadings of measurements, inconsistent recording of data, mistakes in calculations, and the inability to analyze forces accurately without the use of modern sensors. Original motivations. Newton's third law became the basis for scientists. Scientists researched on how objects exert force from one another. The finding was not an accident, but rather the result of a meticulous work through observation experiments and systematic reasoning of motions. The scientists, engineers, and mathematicians were the ones anticipated the most from the discovery of Newton's third law, since it was allowing a basic comprehension of forces and motions, which in turn was making possible the progress of mechanics, thus the development of technology and engineering designs. Aside from that, the third law of Newton also brought some good effects, such as more accurate navigations and ballistics that allowed for precision in steering ships, aiming cannons, and planning warfare. Newton's third law was a breakthrough in the mechanics, and it made navigations and ballistics more accurate. It helped in the invention of new machines, and it set the ground for new areas like space, robots, and contemporary physics. Today's virtual laboratories are highly reliant on the computer systems and simulations, as these offers the users an interactive, safe environment with variable control, real-time data, and accurate experimentations without the need for physical equipment. Digital lab tools, mostly computers, sensors, virtual instruments, 3D models, software simulations, and visual tools are some of the most sophisticated. Contemporary experiments methods still use simulations, changeable parameters, instantaneous data gathering, numerous repetitions, and virtual examinations for the most accurate outcomes. Current studies of Newton's third law have access to computational modeling sensors and even virtual labs, which allow exact and timely analysis, simulations, and applications in such fields as aerospace, robotics, and engineering. Today's safety practices rely on virtual laboratory simulations and automatic monitoring to greatly reduce the physical hazards, yet at the same time controlling the environments and having digital protective measures in place. The contemporary methods of information collections make us sensors, real-time data collections, software analysis, and visuals, together with simulations for accurate experimental insights. Today, in the field of information processing, computers and softwares are the primarily two tools used to perform effective analysis, modeling, simulations, and visualizations of experimental data. The contemporary studies of Newton's third law are fruitous to sports and motion technology in terms of performance equipment, optimizing safety, and even precise analysis in biomechanics. The study of motions in these fields, such as aerospace, robotics, engineering, biomechanics, automotive designs, and physics, together with precise motions analysis, efficient force applications, and advanced technology developments, bring many benefits. Technology spawned due to this were robotic arms, drones, spacecraft, automatic safety systems, motion sensors, sports equipment, virtual simulations, and collision detection software. Future studies and experiments are supposed to investigate quantum and nanoscale forces, create nanorobotics, quantum detectors, and ultra-precise technologies for health and engineering. The future investigations can probably give us more sophisticated medicine along with the rest of the mentioned fields, energy manufacturers, nanorobotics, computing, and the development of superior and smarter materials.